Hello, and welcome to the Interim presentation for Team 1 for Class ME452, ISD 528. Our team has decided to do analysis and redesign of a 3D printer extruder. Our team members are Andrew Bodeger, Nicholas Brado, Logan Dyer, John Milton, and Joshua Snyder. A 3D printer extruder is the subassembly of a 3D printer that moves the filament, melts the filament, and deposits into thin layers during printing. The one we have chosen to redesign is on the right-hand side and was originally meant to be used with 2 rails and 4 linear bearings. Our primary group is going to be industrial prototypers, and our secondary customer group are 3D printing hobbyists. This is an exploded view of the original design, which allows us to better understand how the parts function.
To better understand part function, we created a fast diagram. The task function is to print material. The primary basic functions are to melt, move, and cool material. Our supporting functions are focused on increasing reliability and ease of maintenance for customers. We mapped the 11 terminal functions from the fast diagram to the 12 parts in the design using a function component mapping matrix. Supporting the positioning of the extruder head is the most frequent function performed in the design. Inversely, the hot end assembly is the most frequent part of the design used to execute functions.
Here we have 2 possible sequences for the assembly of a 3D printer extruder. Each sequence has 4 sub-assemblies, which includes the induction sensor assembly, extruder assembly, bearing assembly, and hot end assembly. For the assembly sequence analysis, sequence 2 beats out sequence 1 in the category of ease of transferring and handling, as well as ease of fastening and joining. This reason is mainly due to how sequence 2 is designed for ease of access, while sequence 1 will have some temporary interference between parts as certain sub-assemblies are installed. Therefore, our preferred assembly method is sequence 2.
This is the bill of materials that was used to estimate the individual and total costs of each part. We found these costs by using the formulas given in lecture, as well as doing some research and making a few assumptions. The total cost comes out to be $132.63. Now this cost is quite high, and this is due to the assembly and the parts not being optimized. There's lots of room for improvement and lots of room to reduce the cost. This is the quad classification chart that was used to guide the redesign of our product. As you can see, the manufacturing cost and the functional importance are either ranked as high or low. Depending on those 2 factors, we get our result. One important thing to notice is things such as the main structure may be classified as keep, but we redesigned it in order to improve or eliminate other parts.
As I said earlier, the 2 consumer groups for this product are for industrial use and hobbyist use. For industrial use, it will have to be relatively high resolution and high volume. To this end, we'll have 4 linear bearings, blowers used to cool prints, and a sensor used for calibration. Hobbyists don't need all of this because they're relatively light volume and workload. So we will have some of these removed or altered, like a lead screw in a single rail instead of dual rails. Functions from the fast diagram were taken and put into the left-hand table and were divided into 2 categories, functions that were the same for both customer groups and different for each customer group. Then, comparing this table to the BOM, we were able to divide all the parts into platforms and modules. The modules, such as the sensors, the blower, and the linear bearings, are for industrial use, while for hobbyist use, these are not necessary.
An example of one such module component is the main structure connector, which couples the extruder assembly to the printer frame. The left image shows the primary design, which has recesses for 4 linear bearings. This results in high rigidity and allows for more accurate parts and greater resolution. The right image shows the redesigned main structure connector for the secondary hobbyist consumer. It has only 2 linear bearings and is adapted to accept a lead screw to be driven. This reduces cost and accuracy, which is favorable for our secondary consumer. Snap-fit assembly is common between the 2 designs, allowing for reduced part count and ease of assembly. The main structure onto which most components are mounted is shown in white and is the same for both designs. This is allowed by the inclusion of snap fits and allows for delayed differentiation in assembly, as will be shown in the next slide. Additional modifications are included to enhance commonality, but for brevity, the main structure is shown only. Through our redesign, most of the parts and subassemblies for the extruder mount directly to the main structure. This allows for differentiation in assembly to be greatly delayed, which reduces assembly cost. As seen in the diagram above, the industrial and hobbyist assembly is identical up until the point of mounting the linear bearings. At this point, the assemblies split and no common parts are used. Given our current design, this scheme is optimal. Thank you for your time, and please contact our design team with any questions you may have.